So now that we've finished our discussions on topics related to the fork join pool and the common fork join pool that's used in the parallel streams framework, we're going to turn our attention to understanding how parallel streams work internally in order to combine results together. And this is a two-part session. We'll first start by talking about how reductions are performed to combine partial results into a single reduced result. And this also is something that appears in the article by Brian Getz, focusing on the internals of streams, basically streams under the hood. And I'll fix the URL again there to update it correctly when I put the slides out. So after the common fork join pool finishes with the apply phase that processes the chunks, their partial results are then combined into a final reduced result. The discussion we're about to have here assumes a non-concurrent collector. We will talk shortly about how concurrent collectors work as well. So it's this joining phase or this combining phase where everything gets stitched back together again. The joins that occur in this phase or as part of this phase always occur in a single thread at each level. So what's happening here, as you can see, is that a parent thread will then join the results from the children threads or thread that is running in the background. And basically things are joined together in kind of a pairwise fashion all across the different apply phase processes or threads. And at that point, the results will be created and then they can be joined further if there's any other joins that need to be done. As a consequence of the fact that joining is always done in a single thread, there's no need for you to put any synchronizers in the collectors that are non-concurrent collectors. So there's no need for synchronization here. It's all done by the way that the architecture of the common fork join pool is used under the hood in order to make things work. So different terminal operations combine partial results in different ways. And understanding these distinctions between the different terminal operations, things like reduce and collect, is very, very important for parallel streams, because it really has an impact on correctness and performance. The way the reduce terminal operation works is it creates a new immutable value by combining the other values that are its children. And remember, immutable just means that once something is set, it can't be changed. And immutable has certain nice characteristics having to do with concurrency and synchronization and so on. So here's a very simple example to kind of illustrate how things work. This is the example from my EX16 folder. We've looked at this before. This is doing the factorial computation in parallel for using a parallel stream and the reduce operation. Just to make everything fit on one slide, we're going to be doing the nth factorial where n is 8. So the way this is going to work, as you can kind of see from the diagram, is we're going to generate a range of longs from 1 to 8 in parallel. And because of the way that the splitterators work, that's going to get chunked up into smaller and smaller subchunks until we get to something atomic. So let's take a look at how this could work. We're going to end up multiplying values pairwise. We multiply 1 and 2. We multiply 3 and 4. We multiply 5 and 6. We multiply 7 and 8. And that multiplication processing takes place sequentially in different threads in the pool. And those create the sub-results you see here, 2, 12, 30, and 56. Then reduce comes along and it combines these two immutable values or two given immutable values, in this case longs, and then produces a new immutable value, in this case also a long. So reduce will take 2 and 12 and multiply that together to make 24. It'll also then, in a different thread, different parent thread, it'll take 30 and 56 and multiply that together to get 1,680. And then the final stage in the reduction is to take 24 and 1,680 and multiply those together to get 40,320. So that's how the reductions take place. And you can see how some things work in parallel, and then their results are merged back together again or combined back together again by using reduce. And every step along the way, two immutable values are multiplied together to create another immutable value. In contrast, and hopefully you remember this from our previous discussions about terminal operations, collect mutates an existing value, which is known by the name the mutable result container, things like a list or a map and so on. And so that means that it expects to be able to change those results. So here's a very simple example. We've also talked about this one before, I believe. This is the program in my EX14 folder that counts the number of words in Shakespeare, in the complete works of Shakespeare. And so you can see kind of how this works. It goes ahead and it gets all the words in Shakespeare, and then it starts splitting those things up into chunks. So you'll have the first half of the words and the second half of the words, and then the splitterator chunks that up into the first quarter of words, second quarter of words, third quarter of words, fourth quarter of words, and it keeps going and going and going until you end up with atomic-sized chunks. And then all those atomic-sized chunks are going to be processed sequentially, but all together in parallel. So the cumulative results are done in parallel, even though each piece is done sequentially. And then we're going to go ahead and start collecting the results back together again. And you can see here in this particular case, we're going to be storing the results into tree sets. So we're going to be using the toCollection factor method on the collector's utility class. And we're passing in the tree set constructor reference, and that will go ahead and create tree sets. And as you can see here, there's actually going to be multiple tree sets created. So the tree sets will be created for the different chunks, and then as collect works, those sub tree set chunk results will be merged together to form yet another tree set. And this keeps happening until we end up with a single final tree set when all is said and done. So each of those tree sets along the way, of course, will be mutated as we add elements into them. And of course, those elements will be done in a way that will be distinct because tree sets don't allow duplicate values. In contrast, and we'll see this later when we talk about concurrent collectors, they work differently than non-concurrent collectors. So you can see with the non-concurrent collector approach, the sub-results are performed in different threads in sub-tree sets in this case. And there's no need for synchronization because nothing's ever merged together concurrently. They're always merged together sequentially. Conversely, for concurrent collectors, as we'll talk about in just a minute, they have a single mutable result container. And this single mutable result container is actually accessed by all the different threads that are all running concurrently or running in parallel. And as a result, it's necessary for the accumulator operation on the mutable result container in a concurrent collector to have synchronization, because otherwise you'd have chaos and insanity break out if you had multiple threads that were simultaneously trying to update the concurrent result container. So we'll talk a bit more about that later, but I just want you to see at a high level very quickly that that's the key difference, that there's only one mutable result container for concurrent collector, and it must be thread safe, must be synchronized, whereas for the non-concurrent collectors we see here, they can have non-synchronized collections that are used to collect the sub-results because they don't ever get called in multiple threads of control. So that's really the main difference. So that's just a quick overview talking about some of the interesting aspects of how parallel streams does combining of elements using, in this case, collect and or reduce. We'll talk more in the next video in this series about other aspects of combining results.